Hello everyone. Welcome to the fourth lecture in the lecture series on convolution code. Today we will be discussing the procedure to find the code vector for a given n, k, m convolutional code using transform domain approach. To begin with, let us first recall the topics that we had discussed in our last session. In the last lecture, we have seen the procedure to obtain the code vectors using generator matrix method. We have seen the procedure to construct the generator matrix for a given convolutional code. The dimension of the generator matrix in convolution codes is not fixed, but it is dependent on the length of the input sequence. There has to be so many number of rows in the generator matrix, as many number of bits that are there in the data to be encoded. The procedure to construct the first row of the generator matrix is as follows. The first bit of each of the generator sequences of the encoder form the first n bits of the first row of the generator matrix. The second n bits of the first row of the generator matrix can be obtained by considering the second bits of the generator sequences, and so on. This completes the construction of the first row. The subsequent rows can be obtained by performing a linear shift on the previous row of the generator matrix by an amount of n bits. That means to say, the second row of the generator matrix is simply a linear shifted version of the first row by an amount of n bits. Similarly, third row can be obtained by shifting the second row by an amount of n bits, and so on. We need to construct as many number of rows in the generator matrix as many number of bits that are there in the input sequence. Once the generator matrix is constructed, the code vector for a given data sequence can be obtained by just performing matrix multiplication of the data sequence with the generator matrix. It is the same procedure that we had used during the encoding operation of linear block codes as well. This is just a normal matrix multiplication in binary. Okay, so this is all we had discussed in the last session. So in today's session, we will see how to find the code vector for a given convolutional encoder in transform domain approach. We know that convolution in time domain is equivalent to multiplication in transform domain. We have seen that the code vector for a convolution code can be obtained by performing the convolution of data sequence with the respective generator sequences. Using this property of convolution, I can even able to obtain the code vector by considering data and generator sequences in its transform domain, then performing the multiplication of data polynomial with the corresponding generator polynomial, so that I will going to get the code polynomial which is in transform domain. From the code polynomial, I can write the time domain equivalent to obtain the overall code vector. Okay, so this is the procedure. So here initially we need to represent all time domain sequences, that is generator sequences and data sequence in its polynomial domain equivalent. Then we need to perform the multiplication of the data polynomial with the corresponding generator polynomial to get the corresponding code polynomial. Once all code polynomials are obtained, individual code polynomials are obtained, we have a formula to find the overall code polynomial v of x. If I know v of x in transform domain, I can able to write the time domain equivalent of this, which gives me the code vector. Therefore, the procedure is as follows. we need to first write the generator polynomial, which is nothing but the polynomial domain representation of the generator sequence. Then from the given data, we can even able to write the data polynomial, perform the multiplication of that data polynomial with the generator polynomial to get the corresponding code polynomial. Finally, the overall output can be obtained using this formula. Here n represents the number of output lines. Okay, so therefore if n is 2, if we have only 2 output lines, then the corresponding overall polynomial v of x becomes v1 of x square plus x into v2 of x square. If n is 3, then v of x becomes v1 of x cube plus x into v2 of x cube plus x square into v3 of x cube. Let us now take up an example. We will consider the same encoder that we had considered for all our previous cases. We will take up the same encoder and we will try to find the code vector for the same data sequence, and we will see whether we will going to get the same code vector using transform domain approach or not. As already mentioned, the first step is to represent the generator sequences in polynomial form. So the generator sequences were 1, 0, 1 and 1, 1, 1 for the given encoder. The corresponding polynomial representations are g1 of x becomes 1 plus x square, 1, 0, 1. Okay, so that is equivalent of writing 1 plus x square in polynomial domain, and g2 of x becomes 1 plus x square because g2 was 1, 1, 1. The data that we had considered for encoding in the previous cases was 1, 1, 0, 1, 1, 1, 0, 1. So we need to write the polynomial domain representation of 1, 1, 0, 1, which is nothing but 1 plus x cube plus x to the power 4 plus x to the power 5. Then find the individual code polynomials v1 of x and v2 of x. v1 of x is u of x into g1 of x. Multiply both polynomials. It is binary. Therefore, x cube and x cube gets cancelled. X to the power 5 and x to the power 5 gets cancelled. So we will get v1 of x as 1 plus x square plus x to the power 4 plus x to the power 6 plus x to the power 7. Okay, so if I write the binary equivalent of this polynomial, this should be equal to the sequence v1 which I had obtained in time domain approach. Okay, so if I write the bit sequence equivalent of this polynomial, I will get 1, 1, 1, 0, 1, 0, 1, 1, which is the same sequence v1 that I had obtained in time domain approach. Similarly, find v2 of x, which is nothing but u of x into g2 of x. Again, perform multiplication, cancel out the terms appropriately, and we will get v2 of x as 1 plus x to the power 5 plus x to the power 7. Here also you can cross verify your answer. If I write the binary representation of this, it should be equal to the sequence v2 which we had obtained in time domain approach. Finally, let us find the overall code polynomial v of x, which is given by v1 of x square plus x into v2 of x square. This expression I have obtained by substituting n as 2 in the general expression that was given in slide number 4. We know v1 of x, we know v2 of x. Replace x with x square to to get v1 of x square and v2 of x square. Then substitute them in the formula, simplify, and get the overall code polynomial. Finally, we can write the binary equivalent of the code polynomial. Here the length of the output can be calculated as follows. We have two output lines, so we will have two outputs v1 and v2. The length of the first output v1 is given by length of the data sequence plus length of the generator sequence minus 1, because it is linear convolution, right? So length of the data is 6, length of the generator sequence is 3, so 6 plus 3 minus 1 is 8. So v1 is of 8 bits. Similarly, v2 is also of 8 bits. Therefore, the overall code sequence v will be of 16 bits. So write 16-bit equivalent of the code polynomial v of x. And it can be observed that the code sequence v is same as that of the one we obtained using time domain and matrix approaches. Now we have come to the end of the current session. Let us recall the topics that we had discussed in the present lecture. We have seen the procedure to find the code vector for a given convolutional encoder in transform domain approach. Firstly, we need to represent the given generator sequences in its polynomial representation. We have to write the polynomial representation for the data which is to be encoded. Then the individual code polynomials are to be obtained by just performing the multiplication of the data polynomial with the generator polynomials. Once the individual code polynomials are obtained, the overall code polynomial v of x can be obtained using the general formula in which we need to substitute the value of n. Once we get the overall code polynomial, write the binary representation of the overall code polynomial. That gives you the code sequence for the given input. For better understanding, I insist you to take up few more examples. You can take up these questions for practice. The first question is to draw the encoder diagram for a systematic 3, 1, 2 convolution code with the generator polynomials g1 of x is equal to 1 plus x square and g2 of x is equal to 1 plus x square. So it is a systematic code. A similar problem we have solved in the last session as well. It's a systematic code. Therefore, one of the output lines should have been directly connected from the input. So here n is 3, k is 1, m is 2. So out of 3 output lines, the generator sequences for 2 of the output lines have been given, corresponding to output line 1 and output line 2. g1 of x and g2 of x are given. g3 of x is not given, but it is given that the code is systematic. Therefore, the third output line is directly connected from the input. Also here the generator sequences are not given, instead generator polynomials are given. And we know how to write the generator sequences from the generator polynomials, right? g1 of x is as good as writing 1, 1, 1. The corresponding generator sequence would be 1, 1, 1. Similarly, for g2 of x, it is given as 1 plus x square. Therefore, the corresponding generator sequence would become 1, 0, 1. Then the second sub question is to obtain the output for the input sequence 1, 0, 0, 1, 1 using transform domain approach. Recompute the code vector using matrix approach. Verify the answer with time domain approach. So for that particular data sequence, you need to obtain the code vector in all 3 approaches. Okay, and you are expected to get the same sequence in all 3 cases. These are the few references that are used in preparing this presentation. This is all for today's presentation. In the next session, we will be discussing about the various ways of representing the convolution codes in general and state diagram representation of a given convolutional encoder in particular. Okay, so for better understanding of today's discussion, I insist you to solve more problems your own. Thank you very much.